Now that we can visualize complex numbers in the complex plane, there are two important numbers associated with a given complex number called the modulus and the argument of a complex number, which are eventually going to allow us to write complex numbers in new ways. Let's look at the modulus and the argument in turn. We begin with a complex number z equals x plus iy in the complex plane. Then the numbers x and y correspond to the real and imaginary parts of it. The line joining the origin to the number z plays an important role in the development of complex numbers, and the distance from the origin to z is called the modulus of the complex number. And we can see from the geometry of the picture, the modulus is equal to the square root of the real part squared plus the imaginary part squared. So this length is x and this length is y, meaning the hypotenuse is the modulus of z. An alternative way to write this is the real part squared plus the imaginary part squared, all square rooted, which in fact is the square root of z times its conjugate. And it's just the distance from the origin in the complex plane. It's always positive, and of course it's a real number. In fact, it generalizes the function, their absolute value, for real numbers. So when y is equal to 0, this is just a definition of the absolute value function. So if we want the absolute value of 1 minus I, so this is the square root of 2, and that's the same as a modulus of 1 plus I. Quickly just note where they are in the complex plane. It's always useful to have a quick drawing to go with any complex number you see. 1 minus I is down here, 1 plus I is up here. Those are conjugates of each other. Note that the modulus of I is the square root of 0 squared plus 1 squared, so that's just equal to 1. The distance from I to the origin is 1 unit. We've seen that z is a real number and the modulus of z is greater than or equal to 0, and in fact the modulus of z is equal to 0 if and only if z is a number 0. We also have z bar is a modulus of z squared, and that implies actually, if we go back to dividing by numbers, 1 over z, the conjugate of z divided by the modulus squared. We've also seen an example where the modulus of z is the modulus of the conjugate. Geometrically that makes sense because the modulus and the conjugate are just reflections in the real axis, and so therefore the distance from the origin doesn't change. Another useful thing to remember is that the absolute value of z minus w is the distance between two numbers in the complex plane. So geometrically we can see this as follows. If we take two numbers, z equals a plus ib and w is c plus id, form the line between those, and let's just sketch on some distances in here. The change in the distance between z and w on the real axis is c minus a, and the change in the vertical axis is b minus d. And so therefore, using the distance formula, we just have the modulus of z minus w is the square root of a minus c squared plus b minus d squared. There's some other important properties of the modulus. The modulus of z times w is equal to the modulus of z times the modulus of w. And to see this, what we can do is calculate the modulus of zw squared. And using what we had before for the conjugate, we have this is zw times zw bar. So the modulus squared is a complex number times its conjugate. Using properties of the conjugate, I can write this as zw z bar w bar. Then I can regroup the numbers, modulus of z squared times the modulus of w squared. And so you can use this then to prove things like the modulus squared is equal to the square of the modulus. Let's now have a look at what's called the argument of a complex number, or the phase. Again, we start with a sketch. Take a generic point, z, and draw a line from the origin to it. Now we've seen that the distance from the origin is the modulus of z. Another part that's important for this number is the angle made with the real axis. So this angle in here, theta. This is called an argument of the complex number. Now, a peculiar thing here is that I've said it's an argument, it's not the argument. And the reason is because it's not a unique assignment. I can add on multiples of 2 pi in order to specify where the point z is in the complex plane in terms of locating the line joining the number z to the origin. Let me just give an example of why this is the case. Let's take the number z. Now we've seen that the number theta from the positive real axis anti-clockwise to the number z is an argument. In fact, it's called the principal argument of the number z. But I can specify where z is, or which line it lies along, by doing the following. Let's say instead of just going up to z, I go all the way around and then up to z. That's a perfectly valid way to specify the argument of z, or an argument. I could go around 2 times, I could go around 3 times, I could go around 100 times. Alternatively, I can go around the other way from the positive real axis. I can go around this way to specify the number z. These are all valid ways to specify where z is. Theta plus 2 pi is an argument, and so is theta minus 2 pi. So in fact, we need the notion of a principal argument and then all of these other ones. We're actually going to see that these other ones play quite an important role in the formulation of complex numbers. It's not just pedantry. So in fact, we define the principal argument is the angle such that theta is between pi and minus pi. So a negative argument just means that I'm going around clockwise rather than anti-clockwise. So for example, I might have a number down here and this principal argument, which is negative, heading off below the real axis. So the principal argument is the argument that lies in this range, and we specify the negative real axis with an argument of plus pi rather than minus pi. The set of all arguments is written as argz, and it's defined as a set, so we're going to use set notation. It's the set with the principal argument plus 2n pi, where n is the set of integers. So n is in z, it's a set of all integers, and the set notation means that it's an infinite number of values. Let's do a few quick examples to see what sort of arguments we get. Z equals 2. These are always easiest if you draw a quick diagram just to locate it in your mind's eye to see where it is. So arg of 2 is 0 plus 2n pi. So the principal argument of 2 is 0, and I can add on multiples of 2 pi. Z equals minus 2. Again, let's just locate it in the complex plane. So we have a number on the negative real axis has a principal argument of pi, and we add on factors of 2n pi. And for consistency, we'll write it in the set notation like so. What about more complicated numbers? The argument of I, this is equal to pi by 2. The principal argument is just pi by 2, and we can add on multiples of 2 pi, and minus I is just located, and here by 45 degrees, minus I is minus pi by 2 plus 2n pi. And I've been a bit sloppy not to write out the full set notation. A slightly more complicated one, z equals minus 1 minus I. Now to work this out, again we need to sketch it in the complex plane. How do we do this? Well, we need to figure out what all the angles are. So there's the principal argument is the angle from the positive real axis to this line. Given this angle in here is pi by 4, this angle is 3 pi by 4, and so arg, the argument, the principal argument of minus 1 minus I is minus 3 pi by 4, the minus signifying that I'm going clockwise. Another argument, which is perhaps one that you might have initially thought of, would be this angle in here, which is 5 pi by 4. That's an argument of the number 2, it's just not the principal one.